welcome. Thank you for joining this new series of seminars on manufacturing. This fall session is dedicated to exploring together frontiers of manufacturing technologies. And today we have the first speaker, Dr. Elias Shakour. Before we give the floor to Dr. Shakour, I would invite Professor Judy Jin, the Program Director of Manufacturing, to say a few words.
Okay, thanks, Miki. Okay, so first I'd like to welcome to join our manufacturing seminar series. It has been stopped since the COVID last March. Okay, so I really feel excited we come back for this manufacturing seminar series. So as Miki put a lot of efforts on that to help, especially on this special, the hard environment. So our seminars will be hybrid. So some speakers come in person, like today. Then some speakers probably still in the remote. Okay. So for people to come in person, so I really encourage the attendees to come, so to have opportunity to meet our speakers. Okay. And this is same as Mika just mentioned. This semester we are encouraged about emerging manufacturing technologies. So that will give a broad perspective from academia and also industry people. What are the challenges and the future or emerging manufacturing techniques? Okay, so without further ado, so do you need to further introduce? Yeah, introduce the speakers.
Thank you. So today we have the honor of having Dr. Elias Shakour, our first speaker. Dr. Elias Shakour graduated from Michigan State University, and sorry, but he is here, so it's good we convince him to be with you, Vam. And also had business studies. So together they enabled Dr. Shakour to become an innovator of composite technologies. Dr. Shakour works in the composite group. He's the team leader for the composite groups in BSF. BSF is a worldwide material supplier and tier one, and all the innovation in lightweight materials are coming from BSF. Today, Dr. Shakour will talk about two of the, I should say, most important innovations in his group about two technologies to create high throughput composites. And here, with this word high throughput, probably most of you know, or you will hear in one of the classes. I think it's a global manufacturing class. High throughput in composites is one of the challenge. As we said, we'll explore the frontiers of manufacturing technologies in this fall. And high throughput for advancing composites in mass production, it is one of the frontiers, and we'll explore today, together with Dr. Shakour, which are the solutions to go beyond. Okay, thank you.
Thank you.
I think you have your...
So I can speak, everybody can hear me? Yeah. Well, good morning, and thank you again, Dr. Bano and Professor Judy. This is a privilege for me, so I'm happy with that. Actually, I got an email from Yoram Koren asking me, he prefers to be in 3D and wishing me luck, so at least I got the energy now to come and talk to you guys, so thank you again. Today's talk, exactly, I'm going to talk about, so I work at BASF. It's a chemical company. We sell chemistry. We don't make composites, but we have to support composite applications. So our tier and the automotive industry, I work to adapt to it. So I work closely with the automotive industry, and I want to replace metals, nothing against metals, but if we find the way to reduce weight, we want to reduce weight. So BASF here in Wyandotte, Michigan, it's the head center of the R&D in North America. And we have a lab that it is a composite lab. And it's a kind of a sandbox, and it makes a prototype parts. And the idea is we want to have our customer come in, bring their tools, and make a part, make the good part, and we will help them with that, and then go back and make a production. So keep in mind, this is a prototype, so actually we make actual parts, but always in our back mind, we need to be in compliance to the volume and the prices and the weight. There is lots of specs that we have to be in compliance with. Although we don't do that in production, but we have to be in compliance, so our customers, the tier or the OEMs, has to be in, comfortable with. And that's where I'm going to introduce like two technologies that we think it's a breakthrough in composite to make composite as a high throughput. So this is the main talk today, and please stop me anytime if you have any question. So as I said, we have this lab, and really BASF really works in all spectrum of composites. And, from injection molding, we do like, small pellets that have a small short fibers. But our team is really focused in this area, the area of high toughness, high strength, and high strength and stiffness all together. And the reason is we want to utilize the length of the fiber. The longer the fiber it is higher strength. Yeah. So there is, for each fiber size, there is a technology that to manufacture that. Now, you can see it on the lower bottom, but I'm going to focus on two technologies that we think it's a breakthrough in this area, which is pultrusion and spray transfer molding. Now, pultrusion, you might say, why pultrusion? And if I look at this graph, eventually pultrusion, it shows me the highest strength or tensile strength, and the reason it has a higher volume fraction of glass fiber. So it's tempting. And if you compare those numbers to the high strength steel, I am there. So this is really good. So I'm comparing this to steel. This is much lighter, but yet it gives me the strength. So that's one advantage. The other one that we looked at is the RTM, or what we call high pressure RTM. Now, high pressure RTM was in the industry. They like it as automotive, but it doesn't give us enough parts per year. And they're not happy with that, because if you think about the Ford and the Toyotas, with those big cars, like they make 150,000 a year. So 40,000 doesn't fit. So that's where we said, let's focus on the pultrusion because it's a high strength. I can really look into how I can accommodate that as a high throughput, and we'll talk about it. And also, there's a technology that we adopted and we developed. We call it STM, and I'm going to talk about it more, which is spray transfer molding. Now, high pressure RTM, I don't know how much you know about that, but high pressure RTM, it's eventually resin transfer molding. So that means I have a resin and I will inject that resin into a cavity. To do that, I need to have layups with the fabric. I have to put it in a tool to preform it to have it almost the same shape that the end part. Once I have it stabilized, I will take it, inject in high pressure. And remember, fibers, like we're talking continuous fibers. So when I do inject, some of the inlets could be on not the top, but the side. So this could be distorting the fibers. And then we wait for it for curing and demolding. So that's the whole process. But eventually, you can see it's 2 steps. That means every step is a cell or a production place in the industry. Now, I just lay down like what the disadvantages. So if I spray, and you can see it, if you spray, sorry, not spray, I'm saying spray, but you inject urethane, which is a liquid, on a dry fiber, think about it. High pressure coming into that inlet. First of all, it's going to start pushing the fabric away because it's a high pressure. So I don't get the benefit of continuous fiber as we speak because it is a bit distorted. The other thing is the cycle time is not there yet. It's like 3 to 5 minutes. We need to look for a low viscosity, the lower the viscosity, because the tool itself, this is a simple tool, but parts are complex. So we need to look for alternative. Yeah? So the alternative comes, which is like what we call it spray transfer molding. This is a technology that the equipment is like metering system. That means I have to have the liquid chemistry. When I say liquid chemistry, I have an A and B. They come together and they start reacting, yeah? So I have the equipment. I have a robot. the robot will be the center of this application. I'll explain how. We need to have a low tonnage press and a simple tool. So eventually, from a cell equipment, it's much cheaper than having high pressure RTM. But from what it does, it makes a lot of impact. I'm going to play this video and you can see what's going on. So I have a robot. The camera is on the robot. So the robot comes, grab the glass fiber, as you can see here. And now the robot will give a command to the spray to start spraying. And we program where we want to spray. And actually, in the other side, I can also spray a glass fiber. So look at it. I optimize the spray. Look at it's now going around like the pinch edge. So eventually, I can control where I want to put the spray. Not only that, I don't have lots of scrap. And it is in 90 degrees, if you notice. So eventually, I don't distort the fibers. So there is lots of advantages that we can benefit. Now, if you notice, this is a honeycomb. So this is a technology of making a honeycomb load floor that we're adapting it to make more of a composites part. Now, the robot goes to the press. There is a tool in the press, of course. Then the robot closes. The tool closes, the robot gets out, order the press to close. So eventually everything is controlled by the robot. The robot talks to all those stations. And if I don't like the outcome, I can go back to the software, change the spray pattern, and get back. And I will show you some pictures. So all in all, as you notice, is like we take an empty dry fiber and I spray it on top 90 degrees. That gives me an advantage. The cycle time that you saw here, part to part, is 90 seconds. So I'm saving from 3, the minimum, to 5. I'm starting from 90 seconds. And even in 90 seconds, you saw the robot here spraying one side. We can have the robot put 2 spray heads that they can spray in both sides. So I can cut the cycle time much more. So there is lots of advantages in this technology. So, and the other thing is I want to say, this is high pressurized, atomized urethane that gets into the glass fiber. So it penetrates well, it impregnates it well, I impregnate locally, and I can spray from 30 to 100 grams per second. It depends. Right now, I'm only spraying 30 grams per second, and that's enough. Oops, sorry, you saw that. So eventually that goes back, I'm ahead with the slides, is like, as I said, it's really localized wetting, and we're emphasizing on that. I program my robot where to spray and how to spray. And keep in mind, you need to know some knowledge of the urethane or the liquid, how it's going to flow in the mold. So that gives you an advantage, yeah? Because I don't want to spray places that the flow, it's going to go in the cavity and stuck there with a lot. So I have to spray more in certain areas, less in other areas. I have that option. And I will show you some parts. So this is a huge part. When you come to my lab, you will see it. It's underbody. It's about 1.5 by 1.6 meters size-wise. And it has the corrugation because this is a tool we made. We wanted to go after like the truck beds, if you notice, and the underbody of the car. The truck bed, if you notice, they are corrugated kind of a thing. The first run, we did the sample spray. Yeah. Oh, sorry. Yes, this is the latest, but this is the more. So if you notice, I sprayed first, and if I enlarge, or you can come see it, you see lots of gaps here on the edges, and it doesn't cover those gaps very well, while I have lots of urethane in the middle. So what we did is we really went back and optimized the process. And I have more urethane sprayed on the upper side, less urethane in here, by changing the height of the robot, the speed of the robot, and where to spray. So I got the perfect part. It's beautiful, actually. I always call it beautiful part, but it is good part. So we know, like by optimizing, it gets you where you want without really distracting the fibers. So where can we go with this technology? I have a small video on that. So as I said, the honeycomb application, that's where we started. That's the part in your hand. It has a core, paper core, and a glass fiber on top and bottom. But we can go and go beyond. We take the glass fiber, change it to natural fiber. We can take the core, the paper core, change it to be no core, and get like more of a thick composites, yeah? You can see load floors. If you have an SUV car, all the SUVs has load floors now. So it's in your car now. Center console, we're working on that. Actually, Julia was working on that with us, and we made some parts with Professor Bano. I'm going to bring those. And when I put skin foam, that means we can add to it. So the beauty of this application, I can add things. Now we call this monolithic. That means we're taking the core. As you notice, this honeycomb is so light. It's the lightest of composite. I have the highest stiffness there, but we also can go monolithic rooftops. You can see that in different cars nowadays. Door panels. Seat pans. And we made all those parts, so we have them. We know how light they are. Nice. Oops. So I'm going to go back, and I showed you where can, so this technology can take us to multiple places with a high volume production, yeah? So I'm going to show you some examples that we do right now. This is the honeycomb load floor where we started. You can see it has inserts in it. So eventually I can cut the part to the size I want, put the inserts, all will be put in the tool. So I don't need to do secondary process. All is done in one process, in one cycle. And that's the advantage. This is the part in your hands. This is interesting. This is an exterior part, exterior with a paper core. And they want us to put 500 pounds on a opening of 1 foot square, 500 pounds load. And it has to deflect only 12 millimeter maximum, sorry. So imagine this lightweight, and we're replacing this from aluminum. And we were successful of doing that. And we have to submerge it in water, and it passed like 7 days without uptaking water. So eventually, this technology can be also for exterior, although it is the lightest in paper core. Also, I was telling you, like, we can take advantage of this technology. Like, I want, like, you know, we had an OEM came, and they want to do grain. Actually, funny enough, you think it is like a fabric, but this is all in the tool. We make that in the tool, like the grain. This is natural fiber. We're going to talk about natural fiber, but how we do it, we spray the tool with the paint, and then we make the part. As you saw the process, it will be fully integrated, and a finished part will be with the nice looking that it's ready to be assembled. So this is like, you know, you can add to that. So this technology is not only to make plain parts, we can add to it colors, and we can add like a good surface looking. Also, we can do like, you know, soft looking, like the chairs, that the seats of the chairs, the foam, we can do that as well. Of course, I have to show this picture. This is a seat console. We are comparing to polypropylene, we worked with the Professor Bano. We got the natural bamboo fibers. This was 900 grams almost, and this is ended up to be 254 grams. It's much lighter. I'm going to bring it. I forgot to bring it, sorry. But if you find the rigidity, it's much stiffer than the actual polypropylene because it has a honeycomb, so it adds stiffness to it. This is a project with Professor Bano, but we're trying to find like also a home as well in the automotive that we are talking with. Same concept. And here actually we, in the tool, you cannot see, we add inserts. Those inserts, like, 3D printed right now, but those inserts can be incorporated. So eventually I can add attachment. Now, this is the underbody. I just want to tell you, this is a monolithic. That's where I want to have your thoughts and bring up new ideas. This is like composite, pure composite versus, and we have to pass impact testing. I'm showing you like a DART test, like high energy impact test. And you can see like with the 65 joule impact, it did not penetrate. So eventually that's where our OEM, they were happy to see that. This is for underbody, as you can see here. Yeah. And they ask us like, oops, which screen you guys see? Oh, this one, because I have two screens different. So this is the threshold they want us. And as you can see, we can match it. This is the protrusion, the protruded part I talked to you. It's really outstanding. That's why we like to work with that. I will mention it more. But eventually we can make the part pass the threshold of energy absorption in composites. So all in all, this is a technology that can fit multiple applications for automotive lightweighting. Now, this is not enough for us. We are really interested in sustainability, and that's where we want to drive the new technologies. Sustainability is very important for BASF, but eventually it's globally, and we are interested to get into that field. With that, we are trying to experiment with bamboo, as I showed you before, but we have more interest to grow that business. Jute and flax. Bamboo, as you know, it's like it grows so fast that it's in abundance. So we're not here making payment punishment to the nature, rather than the more you cut it, the faster it grows. So there is lots of values. It has low density, and of course LCA. It has a good LCA benefits. As you can see, I need it to be non-woven, like this kind. This is a flax. So if I can create those in a non-woven fabric, I can utilize that. This is the bamboo. So bamboo, we're working with Professor Bano. We're getting the bamboo. We're finding a great value because we're comparing different species, and bamboo is really, I will show you the graph, is giving us a good performance, and that's very important. So I don't need to use bamboo a lot. I can use it on the outer surface to give me where the most deflection is, to give it the benefit of the fiber itself. And the bamboo, I can get any length of fiber, as Professor Bano promised me. So I hope we can still do that. Of course, like with jute, this is non-woven, so we're adding basalt as well. Basalt, which is a net, small net. I don't want it to add weight. Basalt, the density is a little bit higher, on the higher side, but we're trying to be conservative, but add to the strength to it. If you compare, jute, basalt, the minute I have basalt, I increase the strength and the stiffness for sure. But here's the nice graph I'm proud of. This is comparing a glass fiber honeycomb that we made versus the bamboo fibers that we got from University of Michigan, and we compare 4-point bending. Actually, this test was done here, and the stiffness is close enough, and the strength is way on the same level. This is encouraging because I can now think about structural or semi-structural application and implement that. I already presented some of this concept to the tiers. They want the bamboo, but I cannot find it. It's still in a low commodity, but it has an opportunity to grow. And one of the things they were worried about, because it's natural fiber, how does it behave when it touches water? Because application, it has to be exterior. So we put it in water, and actually our customers put it for a longer time. It did not uptake water, and the reason is, which I believe is the urethane, which is a liquid with a low viscosity, it encapsulates the natural fiber, so it does not allow it to uptake water. So there's advantage to that. So you can use it without fear that it will not take water, and it is important because you don't want to drive a car and then your part will start swallowing because it's raining. So we also made internal, this is internal study and it's not external, so we cannot publish it because, with LCA, it's really a science by itself. But this is our internal study that we compared like one part, same part, polypropylene made versus the spray transfer molding. And you can see like the impact on environment is much lower versus polypropylene, although polypropylene is recyclable. Yeah. So, and the reason is with our polyurethane that we put it also has a biorenewable content. So that's one thing. And also the natural fiber. So all in all, we have a better performance on LCA because of the sustainability or the biorenewable components that we have in there. And as you can see, this is a good technology to continue on, and that's where we're promoting, especially like a company like Ford is really happy with sustainability. With that said, this is not enough. So we need to look for new opportunity, and that's where I'm presenting like the new concept to see like where it lands, because we started with some ideas, but eventually we want to get your thoughts and a partnership if there is opportunity like that. One thing is we're working heavily, and we have a team working in battery tray, battery cover, and all of these things. And we're looking into thermal management. That's one of the issues, like they call it thermal runaway. They want to reduce or to have a material that doesn't has a good thermal management that doesn't allow the heat, if there is a burn inside the battery box, to go to the compartment. It asks us, like, first of all, to give us like notification that there is a fire. Also, if the fire from inside, they want it to be contained inside, and if it's outside, not to go to the inside. So we tried with aerogel. This is a material we used to have, but not anymore, Slantex, and we did the burn. I did some testing, but this is one way, but there's opportunities on different materials that has a higher thermal conductivity that can allow thermal runaway for transportation. I can show you with this material, we were happy to see that the same material, this is a 15 millimeter thickness, the top side was about 300 degrees Celsius, while in the middle side was 300 degrees Celsius, while the top side was about 64. So this is really nice, although it was under like burning. But this is not the actual test. We're doing the actual test, but that gives us good indication that we can go forward with this kind of material. But this is still the first couple steps, I would say, because there is lots of opportunity to improve and work on, and there is lots of opportunity here. The other thing that we always look into, like, with composite, it's, yes, lightweight and everything nice, but we need functional composite. Like, we need some composite, the part itself, to communicate and alert me, maybe to communicate from outside, also to give me an alert if there is a damage. So that's where we think we highly want to invest in sensors and detection of failure and so on. So there is opportunities in this area as we speak. This is like a sensor we have tried, and it's in Germany, but it's like we look at the video. They try to pinch.
Yes, it works.
Yeah, there we go.
Oh, sorry.
Oh, but now it's back.
So they try to pinch and it will start telling us where is the failures. If you can look into the upper side, they pinch it like to damage it, and it will tell us what square it is damaged. And This is a start of the study. I mean, it's not complete, but this is where we want to be going in this technology. With that said, this is all spray transfer molding. Now, there's another technology that we think we are working on, pultrusion. And I showed you why pultrusion, because of the strength. Pultrusion historically is an old technology, so I'm not bringing anything new, really. Now, I want it to be new because it is an important. So the part that you saw somewhere there, where I forgot, where is it now? Yes, this is actually just this year. This is a part in the car. And I will show you this slide. That's a pultrusion part. This is a breakthrough. I mean, yes, automotive, they use pultrusion from here and there. This is a high volume car, the Jeep Grand Cherokee, and it's taking a major role of getting an impact. And I will show you this slide. So pultrusion has opportunities in the automotive, although we're talking high throughput, but it is a slow process in terms of, like, you know, the how you get the material. But if we do the calculation, it is okay process, but we need to add to it more value. So pultrusion, eventually you have a dry fiber. If you're not familiar with that, dry fiber, can you see the cursor? Yeah. The dry fiber comes to a place called injection box. That's where the material, we do the impregnation. The injection box is designed to have like high pressure so we can get a good impregnation. And then it goes to a die that has a cross section. That die, it's heated in different three to four zones so you can get end product. But the advantages is, like, I get high strength. The disadvantage, it's only one cross-section profile that we can get, only. As you can see, we can implement that in different places in the car. We did the study. You know, before we go into any technology, we're, you know, with companies, they like to do innovation, but innovation that has a value in the market. So that's you know, anything we have to show the business case, how this could be penetrated to the market. So there's like opportunities there. Now, as I was telling you, this is the pultrusion on all roving. It really can compete with the high strength steel. Yes, it does not have the same stiffness as you see. It's enough like magnesium, but it's not enough like aluminum or steel. But if you saw that part I gave you, the inner part is pultrusion. The outer part is overmolded PA6, and that gives us the stiffness. Not only that, it gives me a way to do joining. So I have a way to increase the stiffness. So I'm pushing this graph in the left direction to give me more of the stiffness, and yet to be like add parts to it. As I said, it's a fixed part. Cross section, this is like a seawall we worked on. This is like a hat. So eventually we found this is a good opportunity for automotive to replace metal, and you can see that. But to get the automotive to be convinced, we needed to build that in a simulation. And right now we don't have the right material card to do that. So what we do, we need to build a material card. So we did a study on building a material card. And the material card is really focusing on post-failure, the dynamic behavior of the material, high strain and so on. So we did like multiple fiber orientation. As you see, this is all roving. I told you, like all like fabric, all coming all together. We did biaxial. That means we took a fabric that has 0.90. We wanted to compare that. Also, we did a hybrid, like, you know, in the middle is all roving, but the outer is a fabric. And we did the uniaxial, which all fabric, but uniaxial, like it's only zero direction. Yeah. And we did batteries of testing. We invested heavily, but the outcome of this result, I like one graph, that slide, that I always like it, because, you know, we did impact, like the hat part that you saw in the first picture. If I do the impact test, this is the graphs, all of them overlap, almost the same energy impact they absorb. But look at the behavior. And this is interesting. So if for all roving, you know, this is a hat that has a, so the walls collapse, the bottom side of it stays. Eventually the part did not fail fully. It has still resistant in it, yeah? So that's all roving. And when it bounces back, you can see it bounce back to be like, the walls are broken. But when you look at the finished damaged part, the lower surface and upper surface, I still have a flat panel. So this is nice. Now, the biaxial, which is, I told you, fabric of 090, we thought it's going to be better because, for torsion application and so on. Look at the failure. First of all, the failure is like a V. And yes, the wall did not collapse, but eventually there, when we saw the part after, it was all cracked, damage all around except of the lower surface. But total different failure, yeah? Now, let me show you the hybrid. The hybrid, to remind you, it's a fabric 090 that it is wrapped around, and in the middle, it's all roving. Is resisting it, it's not collapsing, and here's the beauty. Look at that after the impact. Bounces back. It's almost like a metal. It's so impressive. Same volume fraction, same impact, same energy impact, but this did not fail. Look at it. It's beautiful. I mean, I'm amazed. The uniaxial, so that's where we start thinking. This is biaxial, so this is where we start recommend and look at opportunities, because this can absorb impact and torsion, and yet it behaves like metal. Although we're trying to replace metal, but we like the behavior of the metal as well. Yeah. So the uniaxial behaves like all roving. There's no advantages in there, and it's more expensive. So that's out of the picture. So this is like we build a material card. With the material card, we really, we were challenged to do testing 23 degrees, 80 degrees, and minus 40 degrees. That's how automotive wants all the time. All temperature, how the material behave. And really, we could compare the actual testing to the prediction, and we really could make it. And that's where we presented that to our partner, LNL, and they went to, then it was FCA, now it's Stellantis. And that's where we were able to get this part, which we call it a tunnel reinforcement. It sits here, and it is made to get an impact. We're replacing metal. We took 2.3 kilograms out of the car, but yet we increased the impact testing and impact absorber much more. So, and we just got the award from Altair Award, and today they're presenting it for the Chemical Society, the SPE, to get another award. It's all about awards now because publicity is important too in automotive. But all in all, this is the protruded part. This is the outcome part. But, don't limit yourself to what you see here. Always there's opportunity how to incorporate things, to bundle it to get what the outcome. Now, this is nice. Is this enough? No. So the whole idea is we will start working with Professor Bano. Actually, we put a proposal for DOE, but this is the foundation of where we want to go. As I told you, the profile of the protrusion, either it's only straight and the same cross section. But what if I can start working on changing the shape of the part and changing the cross section? And that's where we start thinking of shape morphing protrusion process. Professor Bano has a good approach to it with the adaptive manufacturing based on Professor Koren kind of ideas. But we have the concept, we have the foundation. We didn't get the money, but actually I think this is an opportunity to keep looking into that, because we really put a big thought behind it. We identify an OEM, then we worked with Toyota, if you remember. And we looked at a part which is like a cross-car beam, which is like, in front of you, there is a cross-car beam behind that holds all the tableau, everything. That has to have different shapes, different strengths. So we identify everything. So there is an opportunity that we can manufacture this in an adaptable way that it will give us the right cross-section and right morphing shapes. I think this is where the market would like to. Now, I told you in the beginning, this is a slow process. Slow process is relative, yeah? For, if you do extrusion of aluminum, it's so fast. But for a part like this, is 2 meters per minute I pull. So 2 meters per minute, if you think the part itself is 1.5 meters, so eventually I'm getting a part within 90 seconds. That's still good, yeah? And the part that you have here, you saw the pultrusion, the injection molding is only 20 seconds. They did that in a very fast way. So eventually, we are in compliance to where we want the high throughput, like the high volume applications. So with that, I would say, I showed you some concept of how we do high volume production. We took a technology we call the spray transfer molding rather than honeycomb application, because it is an application that could be fit to other composites. So it's broadening the applications. Actually, and you can see we adapt to the geometry, we understand how the material behave, and I think the road going forward is like sustainability. So that's where we show some of the sustainability application. With that, I would say thank you. I hope I'm complying with the time, but thank you again. And if you have any question, write my email. You can ask me now, of course, but please do not hesitate to call us. The lab is made for our customers to come, but also for you, because we look at the talent as well and opportunities. Thank you.
Congratulations for your award. I think this is very important, and it's important that today will be the word will come through. So we have now, we take questions, but for the online attendance, please ask to unmute, and we'll enable your question to come in the room. If there are questions, I think Martin will look to the online questions, but we take questions from the room now. Yes, please.
Okay. First, I say that's very nice talk. So you have a lot of the new technology coming and also put the future direction there. Okay. So I do have questions. Since the process, like the spray, the process is so complex, then do you feel like how you control the quality over the special variations in the large area or large parts? Is in your company also think about whether have any the in-suit quality control, like during the process, during the production, how you can ensure quality? Because you have a layer to layer.
That's right.
Production, if you until final finished product, probably is already too late. So is there any thought about that?
We thought of that, but we didn't put the solution for it. The only thing we did is testing several parts to see if it's under, they call it knee load test, to see if it passes the spec. But to your point, this is a good point that we should look into that, the quality, consistency of production.
Yeah, I'm thinking if you have the online vision system and also combined with the production.
I like that.
Yeah, operation, the parameters like spray speed, temperatures, or viscosity, and also you have online vision to see how the surface quality will be. So this could be very
I need to write a note.
Promising to control the defects or to compensate the quality, to remove the defects.
And to your point, Professor Judy, we are looking for big parts, and some of it, when we start spraying with the first part, end of it to the end part, it could be different. So that's where we are worried a bit. We know the material can stay in the gel time can take it, but we want to have consistency. So this could be, I like that concept.
Yeah, you also point part to part variation or even batch to batch variations as well. So I don't want to just take too much. We can discuss it later.
We can talk that, yeah.
Come out other audience, yeah.
Yes. So could you please unmute?
To me, Mickey?
Yes, we can hear Daniel. Thank you.
Oh,
Professor
thank
Cooper
you.
has a
Thank you
question.
for a great talk. Really, really interesting. And perhaps following on a little bit from Judy's question, you were talking about sustainability quite a lot. I wondered, are you able to share what sort of material yield you get in manufacturing, and how do you recycle or dispose of the scrap that you generate in manufacturing? And whether or not you have any work or plans to look at recycling of end of life composites when these start coming out of vehicles in 15 years time.
Yeah, so that's a good question. It's always on our mind. Now I work with the urethane, so it's not recyclable, but we're trying to do reusable application to it, to take it, grind it, and to find a reuse. Also, that's where we looked into doing the LCA to compare polyurethane versus a polypropylene. How do I go up? And as you can see, I'm trying to get into the just give me a second. The LCA part of it. So we are conscious to that, and that's where we are trying to implement more and more sustainable or biorenewable parts in the component. Now, even hold on a minute. Let me just get to the slide and then. Okay, this is the slide. So this is like, it shows you like polypropylene, which is recyclable versus non-recyclable material. But we showed like and this is a study we have done, we can share that, but it's like, it's not a third party certification, okay? But we did the study and we have a big unit that works on LCA because we have that a commitment to be a CO2 neutral in 2050 or 2030, I forgot, based on our CEO. But you can look at the PU system itself. It has biorenewable content. We have in the total, at least right now, we started with nothing, and now we're having at least 17% biorenewable, and we're thriving to get into higher percent of that. And yet, that's where we want to work in the bamboo and other natural fibers, so we can get a part that about 60 to 70. If we get 80%, that will be great, or sustainable. Now, if that's recyclable, no, but it will be a sustainable, yes.
Yeah. Thank you.
Other questions? If not, would like to. Yeah.
Mickey, I have a quick one.
Sure, please.
Just with you mentioning the parts for electric vehicles and battery trays. I'm guessing carbon fiber is a mild conductor of heat, isn't it? Are there any tricks that you can pull to get the conductivity up to be able to
actually
get the heat away from electronics quicker?
We're not using any carbon fiber. We're aware of the conductivity of it, and we're using glass fiber, and I use some basalts, and we're looking, as you saw, like a different like aerogel material, but we're not using carbon fiber, no.
Okay, and does that conduct the heat away from the electronics quick enough, or is that something that you're looking at?
That's we're very in the first stage. Actually, it's a global effort we're having at BASF. We're looking for partners from OEMs and others. But I can tell you, our colleagues in China, they're way ahead of us. Like in China, they're way ahead of us in the battery and battery development. But all what we're doing right now is like identifying different fibers that can, as you say, conduct the heat out of the cell, the whole box itself.
Okay. Thank you.
So we're still in the early stages. If you have ideas, we can take those. I mean, we will not patent that. We'll work with you.
Thank you. So, as a token of appreciation, we offered you a gift from
here we go.
ISD.
That's why I came.
Yeah, sure. So, thank you once again
thank you.
for
Thank you so
being
much.
so kind and.
Oh, sure.
Oh, yeah, sure.
I know my daughter will take it already. Oh,
This is,
oh, I love that. Integrative systems. That's your department.
sure.
Oh, wow. Oh, I love that. Okay, I'm changing to this. Yes.
Okay.
Thank
We'll
you.
see. Yeah.
Here we go. Next time. And I will bring the part. Yeah. But thank you for having me. It's a pleasure, really. And it's always good to get other ideas.
Sure. Thank you for coming. And this is an open discussion. This can continue through emails or a next visit. Normally, we'll have an itinerary following this seminar, but because Dr. Shakour is in a big rush today, he has an important meeting with his vice president. We'll set up another day where we have time to go through the labs and talk about new collaborations. And also, we invite you to express your willingness to visit BSF. It's just 40 minutes or 35 minutes
Yes.
far. I think Julia knows very well. She did an internship last summer there. So, and also one of the graphs was presented here. It was a result of the internship of Julia at BSF and showing the glass fiber versus bamboo fibers.
That's her graph.
And ISD awarded this capstone project, and Julia has this award. Thank you very much.
Oh, thank you.
And we want to see you again.
Perfect. Thank you
Thank you.
so much. Thank you for having me again.